Okay, so let's start again. So today we're going to talk about something slightly different from yesterday. Did this fall off? No. So I'm going to introduce graphical designs, which is one of the words in the title of the course. So today we'll do graphical designs. All right, so it'll take us a little while to get to graphical designs. Probably I'll only be able to get to it in the afternoon. But I want to start by giving you a little bit of a motivation for why this concept makes sense. Okay, so we'll start with something that looks very different, which is random walks on graphs. Okay, how many people are familiar with random walks on graphs? Does anybody know about it? Okay, all right, so we'll just start from scratch as usual and see where we go, okay? So, as usual, we have a graph, G, and I'm going to assume that the graph is on n vertices and e edges, okay? All the same assumptions as yesterday, simple, connected, unweighted, undirected, all that kind of thing, okay? So that's the type of graph we have. And what a random walk is, I'm just going to say it in words first, and then we'll later look at a demo. So what we want to do is, we have a graph, and we want to start at some vertex. So imagine you have like a person standing at one vertex, okay? And then they start to walk on the graph, okay? How? What's the rule? So the rule would be, if you're standing at a vertex, you will move to any of your neighbors with equal probability, okay? So uniformly, randomly, you will choose one neighbor and you'll walk there. Then you'll repeat. You look at your neighbors, and with the same probability or uniformly randomly, you will walk to another vertex, all right? You may walk back to the old vertex because that's also a neighbor of the place that you just went to, right? So you may go back, or you start here and you walk to another place, right? And then it just starts to walk like this. That's a random graph. So it's a random walk. It's called a random walk. So it's a process that starts at one vertex, and that at each step it moves to another vertex, and the rule is just uniformly randomly you choose a neighboring vertex. Is that okay? You can make random walks more complicated. You can say, you can also think of this as, say you have like some commodity that's moving through the graph, and at any place, so for example, currency, like when you move currency through different countries, you can sell and buy and so on. So that's not quite, you could think of that as you could try to do that in a random way, but typically what happens is you lose money, right? So when you sell and buy, or you buy and sell, either way you lose money. So you don't actually move all of the money you had to the next vertex. You leave some of the money back in the old vertex because you had to pay some tax, or not tax, but the exchange rate, right? The conversion rate. So there are those kinds of walks as well. So there are these walks where you lose your goods as you're walking through. But for today, we'll just talk about a place where you're just going entirely from one vertex to another vertex. You don't actually leave any part of you back in the old vertex, okay? So there's something called lazy random walks, which is where you leave half your information in one vertex and you move to the next vertex. You may also have a different kind of probability rule, not just uniformly randomly. You might say, okay, with probability, 3/4, I'm always going to move to a vertex that has some property, right? So there are all kinds of variations, and lots of people study this. This very, very famous thing, okay? All right, so that's what a random walk is. And so what we want to calculate is so we'll see a picture in a minute of a random walk, but let me start with a small picture at least, okay? So let's say we are starting at some vertex, which I will call A, okay? There's a whole graph here, and this A has some neighbors. So maybe this is a neighbor, this is a neighbor, this is a neighbor, this is a neighbor. And let's call the typical neighbor B, okay? So B stands for any neighbor, really. I just picked one neighbor. And one way to think about, so what the walk is doing is it's moving from here to here, and then from there it might move to another place, and so on. So we can also calculate the probability of being at any given vertex at time t. Okay? So think of a probability measure sitting on the whole graph. So we have some measure, which I will call mu, okay? So mu is a function on the graph. So this will be a function that goes from the vertices of the graph to a real number, okay? So at every vertex, we will get a probability. So because it's a probability vector, it has to have some properties, right? So this is my probability measure. This is just a probability measure. And the properties it has to have is that if you sum, so first of all, every mu A, the value of mu at any vertex is non-negative. It's a probability, so it has to be non-negative. But because it's a probability measure, it also has to sum to 1, okay? So that's the other property we need. So we need that the sum of the mu A's over all A in the vertex set has to be equal to 1, okay? So what we want to calculate is not what, so let's call mu sub t the probability measure on G at time t. Okay? So by this, what I mean is mu t of A is the probability of walk being at A at time t. Okay, so we'd like to calculate this quantity, this measure, right? And we always have an initial measure. So the initial measure, the way we start, so in the beginning, the person is standing at just one vertex, maybe this vertex, right? So the initial measure we will call mu 0. This is the measure at time 0, right? And this is, this measure usually, typically, we start in one vertex, or at least typically this mu 0 is A. Mu 0 of A is equal to 1 for some A. So all of the, you're standing exactly at 1. And then everywhere else, of course, it has to be 0 because the sum of the entries in the measure is 1, right? So the measure is just a vector, right? It's a measure. So this, you should think of this mu of t, it's either a function that's taking every vertex to a number. This is the way to think about it. But it has to sum to 1 and it has to be non-negative. Is that okay? So in the beginning, we're starting with this measure called mu 0. All its mass is sitting at one vertex. This is where we're starting. So all the mass is here. And then after one step, you have a chance to move to different vertices. And what we're trying to what we first want to calculate is, what is this mu t of A? This one. Okay, so let's calculate this mu t of A. All right, so how do we do? So here's our goal. So what we want is to derive mu t plus 1 from mu t. So suppose I know the measure at time t, I'd like to know what will be the measure in the next time step. Okay, so let's do the calculation. So what is the probability of being? So probability of being at some vertex. So say at vertex B at time t, or let's just call it A again, at time t. Okay, how do we calculate it? Let's think about this. All right, so somewhere, now this is a different A, okay? This is not my initial A. I just pick some A in my graph, and I want to know what is the probability of being at this vertex at time t plus 1, at time t plus 1, because we're trying to calculate mu t plus 1. Good? Okay, so what's the probability of being here? So first of all, to be at A, it better be that there was some neighbor of A So if this is a neighbor of A, say B, then the probability at time t that you're there is mu t of B, right? This is the probability that you were at B at time t. So this so we take this, and then we also have to multiply that with the chance that it moved from here to here, right? So at time t there is, So you have to look at a neighboring vertex. So let's say this was the probability that the walk was at B at time t. And then from B, the chance that it'll move here is, how will we calculate that? So if you're standing at B, then you will uniformly randomly move to any neighbor of B, okay? So that is the degree of B, 1 over the degree of B, right? So what we want, so the chance that it went to A is 1 over the degree of B, okay? But now you have to sum over all possible neighbors of A, right? So we have to sum over all B such that BA is an edge in my graph. Is this okay? So this is the probability that at time t plus 1, you will be at A, right? So you look at the probability of being at a neighbor at time t times the probability that you went from B to A, okay? Which is this. So this is the part where you're standing at B, you're uniformly choosing one of its neighbors. This is the measure that's sitting at B at time t, and then you sum over all the neighbors of the A, and this will be mu t of A. Okay, so this is, mu t plus 1 of A. Is this okay? This is the derivation, okay? So this is how you calculate the probability at time t plus 1 of going here. Okay, so let's assume that G is deregular. So throughout today, we'll assume, maybe forever, we'll assume that the graph is regular, okay? So from now on, we're not going to deal with non-regular graphs, unless you really want to. So if that is the case, then we can simplify this expression a little bit, right? Do you see this one, what this will become? This will become D, and it'll be common for all the B's, right? I don't have a different expression for different B's. It's always 1 over D, which is that, right? So if that is the case, then let's simplify this. So mu t plus 1 of A will become 1 over D, and that's common, so it comes out, okay? So this will become 1 over D, and then I have sum of mu t of B over all B such that BA is an edge. Everybody okay? This will be the expression if your graph is regular. We can take out this 1 over D, and you get this. Okay? What do you mean summing it D times?
Summation, D is D for each vertex. So the summation we are taking D times.
She's saying there are D summands.
Oh, there are D summands here. That is true. Okay, so let maybe we write this again, BA in E, and this is 1 over D mu T of B. That's what that is, right? This, all I did was change this to D. This is not right?
No, it's correct. I think she's just saying that there are D, when G is deregular, then there are D things.
Yeah, there are D things. Yeah, exactly. Yeah. So there are D things to sum, but the mu T of B may be different for your different neighbors, right? They're not equal. So it's not just one number. You still have to sum mu T of B, okay? But the degree part comes out. So one piece of this block, so this was the probability of being at B at time t times the chance that you went from B to A. This part becomes common for all the neighbors. It's 1 over D, that comes out. But these are all different still, okay? So if you have this picture, so it may be that the probability of being here was 1/8, and the probability of being here was 0, and whatever, right? It could have been all different, so you have to sum them. Good? All right, what is the sum? Do you recognize it from yesterday? Can you use something from yesterday to see what the sum really is? So 1 over D is fine, this part. Can we write it in terms of one of the matrices we saw yesterday? We only saw A and L. So what are we doing, right? So we're looking at all the neighbors of A, and we're summing something for every single neighbor of A. Okay? What is it? Adjacency matrix, right? So this is really A times the old probability measure, but you look in the Ath component of it. Okay, so let's understand this properly. So what just happened is that, so what is the adjacency matrix, right? This is our adjacency matrix. It has a row for every node. So let's look at the node for A, okay? In the node for A, then, everywhere there's an edge connecting from A, you have a 1, right? So these are the different Bs. This is a B, this is a B, this is a B. These are all the things that are connected to A. Somewhere there's a 0, the rest are zeros, right? So if I now multiply this with mu t of, the first vertex times mu t of the last vertex, if I multiply this, right? Then in this answer, if you look at what sits in the A position, just this position, it's going to be this row vector times this column vector that sits in this position, right? And that is exactly going to pick up mu t of B for every B that is a neighbor to A. Is that okay? So up in here, in this position, we will see exactly the sum of mu t of B, where B is a neighbor of A. Okay, so that's another way to write neighbor. You write B tilde A means that B and A are related by an edge. Is this okay? So that's what it is. So this expression, this mu t plus 1 of A is really 1 over D times the adjacency times the full probability measure from before, one time step before, but then you only look at the Ath piece. Okay? So this is what's happening at any given vertex. So this actually implies that the whole mu t plus 1 measure, if I want the whole measure, not just for a particular vertex, then this is equal to 1 over D times A times the measure at time t. Okay, please ask a question.
So I understood that adjacency matrix will fetch only the B's which are adjacent to A.
Correct.
But why are you multiplying by the vector mu t of A?
Why
is the adjacency matrix multiplied?
Oh, no, what this notation means is A is a matrix, n by n, right? Mu t is a whole vector of, it's a measure, so it's size n by 1. So the answer is something n by 1, it's a vector, and I'm just taking the Ath component. Okay, so maybe it's better to write it like this. I'm taking the Ath component of the vector, exactly like here, right? So this is A, this is mu t, and there's 1 over D in the back, but let's not worry about that, okay? So when I multiply these two together, I get a big vector, okay? This is mu t plus 1, but if I only want to know what's happening at the Ath node, I only look at this entry, which is what I mean here, okay? So either we can write it like this, or we can put the A at the bottom. So that calculation was for a single node, and now we look at the entire measure for all nodes, and this is the equation you should get, right? So this is some n-dimensional vector. This whole thing is n by n. It's just a scaling of the adjacency, and this is also n by 1. Okay? Works out? Any other questions? Does that make sense? Okay, good? Yeah. There are lots of things you can do to non-regular graphs. The theory is a lot more messy, and I'll tell you in a second why. Okay? So let's stick with regular graphs. So let's look at, so the key thing is that this matrix becomes important, right? So let's call that matrix maybe W or something. So let's let W be 1 over dA. Okay? And what can you say about this matrix? Let's just reel off all the properties of this matrix really fast. It's just a scaling of the adjacency, right? So it still has which all properties? Yeah, it's still symmetric. So that means it has real eigenvalues. We can order them. Is it PSD? No. Anything with zeros on the diagonal is not PSD. Okay, so PSD, if you have a 0 in a diagonal entry of a PSD matrix, the whole row and column becomes 0. You can think about that. So if the whole diagonal is 0, then the only matrix that will survive is the 0 matrix, okay? So it's not PSD, it's just a scaling of some symmetric matrix. It is non-negative still, yes. So from the symmetric part, so these two properties imply, let's do the symmetry first. What? Question? No? Okay. So symmetry implies that it has eigenvalues, and these eigenvalues, I'm going to call them tau today, okay? Because just to be different from Laplacian and adjacency, let's call them tau. But now, so let's say the eigenvalues are called tau I, and these are real, and we're going to order them in absolute value, okay? So different from yesterday. So I'm going to say the first one is tau 1, and its absolute value is greater than tau 2, greater equal to tau n. We'll see an example in a second, okay? So I'm going to order them by absolute value from the biggest to the last. Good? Okay, it's just a convention. So it has these eigenvalues that we can order, they're real, and we're going to choose this ordering. Good? We'll see examples in a second. Okay, and then because it's symmetric, it also has eigenvectors. So here are the eigenvectors. You can assume they're orthonormal. The matrix is diagonalizable, all that kind of thing, right? Okay, now let me come back to your question. What was your name? Abhay, yeah. So Abhay asked what happens in a non-regular graph, right? So if you have a non-regular graph, then the matrix that we're dealing with is not like a scaling of the adjacency, right? You really have to deal with this piece. So so what's happening here? So you have to divide, so 1 over degree of b is attached to every mu tb, okay? So when you do this calculation, you have to also keep track of which vertex b that you're using, and divide those entries by 1 over the degree of b, right? So what is happening matrix-wise, do you see?
Pre-multiplication of some diagonal matrix.
Say again roughly?
Pre-multiplication of some diagonal matrix with 1 by b.
Yeah, exactly. So what is happening is that you have to pre-multiply the A matrix with 1 over the degree of 1, 1 over the degree of 2, and so on. So these may all be different, okay? And now what property gets destroyed immediately of the properties you just told me about 1 over dA? Symmetry goes away, okay? So it's not a symmetric matrix. You cannot guarantee anything. Real eigenvalues, you can't guarantee orthonormal basis, you can't guarantee diagonalization, but there is a way to get around it, okay? So there's a way to like renormalize this matrix, and then people still go on. You make a different matrix that's symmetric, that has a parallel eigenstructure. So it has a parallel eigenvalue, eigenvector structure, and people work with that. Okay, it's more complicated. So if you want to know about it, you can read about it, but it's not as simple as in a regular graph. Make sense? Okay, so let's come back to the regular graph. So you gave me these properties. All right, so we got the eigenvalues, we got the eigenvectors. They're ordered in this way, please remember. Now, so this part we did. So let's now look at the non-negative part, okay? So non-negative, do you remember what were the properties? Frobenius? We have Frobenius, right? From yesterday. So Frobenius will tell you dominant eigenvalue, and which is positive, with a positive eigenvector, and all other eigenvalues in absolute value are less than this one, okay? All right, so all those properties still work, right? But this matrix has yet another property. Do you know what, do you see it? If I do 1 over dA, the row sum is 1, and the column sum? Also 1, okay? So that's an extra property. So Frobenius implies some stuff, but this matrix is what's called Markov. So A is a Markov, or 1 over dA is a Markov matrix, which implies that the column sums and row sums are what? 1. Yeah, they're both 1, right? because we're dividing, so in a row we have degree many ones, we're dividing by D, so I have 1 over D, 1 over D, 1 over D, as many as the neighbors, which is D, so they sum to 1, okay? So this is called a Markov matrix, or Markov only actually means that the column sums are 1, and this one has column sums and row sums 1, which is called doubly stochastic, okay? So we only need Markov actually to write down what I need, okay? So you can have column summing to 1 and the rows doing something else, that's fine. That's all we need for today. But this one's, because it's symmetric, it has both, okay? It's doubly stochastic. Okay, so if you're Markov, if you're Markov, then Frobenius says something more than just there's a dominant eigenvalue and all the other eigenvalues are less or equal to it. What does it actually? Okay, so let's have the people who don't know spectral graph theory tell me a little bit about this. So yesterday, what did we learn about a regular graph and its adjacency matrix? What's the top eigenvalue? Degree? The D is the top eigenvalue, right? So if you divide the matrix by 1 over D, then the top eigenvalue becomes 1, okay? So the top eigenvalue is 1. In fact, all the eigenvalues will divide by D, right? So the top eigenvalue is 1. So these two together imply that the top eigenvalue, so tau 1 is 1, okay? That's the top eigenvalue. So that's going to be 1. And then what's the range in which all the others lie? The rest of the spectrum. It's the same Frobenius theorem. The top one has become 1. Minus 1 to 1, exactly. So all the other eigenvalues, tau I, they live inside the interval from minus 1 to 1. Okay? So from what we did yesterday, we know already that this is going to happen for this matrix. Okay? So this matrix is called the walk matrix because it comes from random walks. So we'll call this the walk matrix. Of G. Okay, so it has this kind of eigenstructure. All right, so that's awesome. We got that. And, right. Okay, so we saw all that. So now maybe it's time to actually look at some pictures before we continue. So let's get so everybody okay with what we just did? This is going to go behind the screen, but I guess this is the key thing. So that's key. And this is just information about that walk matrix, so maybe that's okay. Okay. Oh, it has to detect and all, right? Okay, it seems to have detected the source. Maybe we can switch off these lights. Okay, so we need to make it a little bigger, right? Okay, can you read in the back? Do you want it even bigger? I'm going to start clicking on it. This is just the script.
150 maybe.
150? Okay. Okay. All right, so this is just, don't worry about the script, okay? I'm just going to click on it one by one so that you can see what's happening. Okay, so in the first step, we are starting with this Thomason graph again that we saw yesterday. Okay, so this is a graph data graph. It gives me this thing. It has some number of vertices. We could ask for it, but let's not worry about it. And this next bit of the script is going to run a random walk on this. Okay, so what it's doing is it's taking, so what I'm calling W there, this script is calling M. So it's taking the adjacency matrix, multiplying it by the inverse of the diagonal matrix, which contains the vertex degrees. So it's the degree matrix. In this case, which is just 1 over D. Okay. So, sorry?
1 over 3. D is 3.
Oh, in this case, it's 1/3, yes. So this is just constructing the walk matrix. Okay, maybe I'll call the walk matrix M, just so we don't confuse. So let's call this thing M. Okay, all right. And then it's going to start a walk. So it's going to start somewhere, and then it's going to do the walk. Okay, so let's actually let me show you the walk. Okay, so I don't know if you can see
The red one.
this red vertex moving around. So we can just look at it for a bit. Do you see it? It's doing the random walk, okay? So at every point, it should only move to a neighbor. And it's going to move with probability 1/3 to one of its neighbors, okay? So that is the random walk. Everybody okay? This is just a walk. Are we good? Okay. So now let's actually look at how the measure moves. Okay? So the measure is a slightly different thing, right? It's calculating the probability of being at any vertex at time t. So every vertex gets some number on it. It's the probability of being there at that time. So you're going to see a number on every vertex, and that collection of numbers will change in the next time step. It'll change again in the next time step, and so on, right? So it's a measure. The measure will be on, I mean, it'll be supported on certain vertices, and that's the next thing we're going to do. So, okay, so this is the measure moving. So you see, there are red dots on multiple vertices. If they are blue, that means that there's zero measure there at the moment. So as time is progressing, do you see what's happening? The vertices are all becoming red, okay? And then eventually, everything is red, and it's stuck, right? Should we do it again? It's starting again. Okay, so yeah, just take a look at this measure. So in the beginning, it started in that corner vertex. And then the measure is spreading. So this is the recurrence relation, this relation. It's calculating mu t plus 1 equal to the walk matrix times the previous measure.
But just to clarify, it's not weighted. It's not giving more. It's just
Yeah, that's right. It's just
coloring red if there is a probability.
That's right. It's not weighted. Thank you. Yeah. So the numbers are slightly different because they have to sum to 1 and all that, right? The numbers can be different. This one is just saying that, okay, there will be some positive probability at all the red vertices at time t. Okay? So this is where the measure is going. And at the end, when it's stuck, it seems like the measure has spread on the whole graph. Every vertex has a probability of being hit. That's what this is saying. Everybody okay? All right.
I have a doubt. You said that for one regular graph, we are multiplying by 1 by degree matrix, like diagonal matrix. So if you multiply, then one row getting the same value, like consider the
Oh, sorry. Maybe then it should be the columns. Yeah, you have to post multiply. Correct. Yeah. So pre-multiply, post-multiply. Figure it out. Okay. So it's the columns that have to take the degree of that vertex. Correct. Yeah. So correct. Thank you. So you have to post-multiply. Yes. But either way, it's not a symmetric matrix. So you're going to get into more trouble, and you have to fix it somehow. And people know how to fix it. This is well known. Okay. Is this also okay? Everybody saw the measure? Okay. So what seems to be happening is, at the end of the day, as Arvind said, these are not weighted by magnitude, but it seems like every vertex has a probability of being hit at the end, and then it stabilizes, and then it starts again. Okay? So here it starts again because of the Mathematica code, but normally it just stabilizes, it stops. Okay? That's what's going to happen to the measure. All right. So that's good. So now let me show you one more picture while the computer is up. We're going to, okay, I don't need that. Let's do this one. So I'm going to put the cube graph back on. This is the cube graph. We saw this graph yesterday. And now let's do the same animation on the cube graph. Okay, watch what's happening. Are you formulating a theorem in your head? What's happening? Just a little louder, please. I can't hear here.
It oscillates between the parts.
Yeah, it's oscillating. It's definitely not converging. Okay? Maybe you don't know that it's oscillating. I mean, you can see it's oscillating. It's actually oscillating between the two color classes. Remember, yesterday we saw that the cube graph partitions. And the partition is exactly this blue partition and the red partition, right? That's the partition. And it's just oscillating from one side to the other side, right? It's not converging. Sorry, I have this fan here, so it's very hard to hear for me, so just speak louder. No, the fan is good, but please just speak up. And I also can't hear generally. So is this okay? So this is, you see, so it's a very different picture from the previous example, right? Where it just converged. It just started somewhere, but eventually the measure spread through the entire graph and it converged, right? So we're going to actually look at what is the theorem that's governing this.
So can we say at a given vertex, mu t plus 1, if it is positive, then mu t plus 2 will become 0?
Yeah, that's right. Exactly. Yeah, exactly. That's what's happening. Okay? Okay, yeah, I think that's all we have for the pictures. So let's go back and actually prove what we just saw. Okay, not for the, for everything. Let's switch it off. Okay, so I'll keep the recurrence relation there, the thing in orange. That is the rule by which you get the next probability measure from the current one. Okay, so this is really important. This is our recurrence relation. Okay, it's a recurrence, right? It's just moving like that. And then, so now let's look at what we saw in the first picture. Okay, so let's define what's called the uniform measure, which is just equal probability on being in every vertex. Okay, so that's called the uniform measure. So let's call it rho. So rho is just the probability vector 1 over n, all the way up to 1 over n. So this is called the uniform measure. Okay? So this is a probability measure, right? It's non-negative, it sums to 1, and it just puts equal probability of being on every vertex. That's called the uniform measure. Okay. So suppose, what happens if we have, at some point in t, suppose the mu t becomes rho. Okay? Some point t, we hit this rho measure. Then what happens, what is mu t plus 1? So mu t plus 1 will be equal to 1 over d times a times this uniform measure. Do you agree? If you hit this uniform measure at some point, then in the next time step, according to that box, mu t plus 1 will be 1 over d times a times the uniform measure, right? So do you see what this is? So this is 1 over dA, and then here we multiply by 1 over n, 1 over n. So in every row, we're going to get, so we still have the 1 over d, and if I do a row of this matrix times this vector, what do we get? D over n. Do you agree? Because in every row there are d ones, and they will pick up 1 over n d times, so I get d over n, and this just comes back to 1 over n. It's a vector, yeah. So it's d times the all ones divided by n, so this will be 1 divided by n, which is the same as the uniform measure, right? The all ones is this bold one that I'm writing, just 1, 1, 1, 1, 1. So you come back to the uniform measure, right? So if at any point you're at the uniform measure, you're done. It can't move again, right? The recurrence just brings you back to the uniform measure and then you're stuck. So that's what you saw in the first picture, okay? At some point it became the uniform measure and then it didn't move again, okay? You got convergence, you have immediate convergence because you started on the uniform measure, okay? Right, so here's like a folklore theorem. I'm gonna put it here. So this is a very well-known theorem. I don't even know who it's from. So it says that at time t, okay, so what we want to calculate is if I start with mu0 and go to mu1 and then go to mu2 and so on up to mu t, is it possible that in the long run we will come to the uniform measure, okay? Is it possible that as you run t forever, you will just arrive at the uniform measure and then of course it can't move again? Okay? That seems to be what we saw in the first picture. In the second picture, it oscillated, so you never hit the uniform measure. But in the first picture, this is what happened, right? In the limit, so if you want to write this correctly, so this is saying that in the limit, mu t as t goes to infinity becomes the uniform measure. So we want to understand when does this happen, okay? Or how fast do you get to the uniform measure? So this theorem says that if you calculate, can you see if I write here? Oh, it's better to write here. You don't care? Okay, please let me know. So, okay, I'll put it here because I want to save this. So it's saying that if you look at the measure mu t, which is a vector, and you look at its difference from the uniform measure, which is 1 divided, which is rho, yeah, which is rho, correct. But let me just, okay. Yeah, rho, good, okay? So if you want to calculate the distance between the current measure and the uniform measure, okay, you take the norm square, because both are vectors, right? I can take the difference and take the norm square. Then this is bounded above by the second eigenvalue of the walk matrix, okay, to the power 2 to the t. This is a theorem. Okay, so yeah, so tau 2 we already said what that is. It is the second largest eigenvalue in absolute value. Okay, but see the absolute value is not important because there's a 2 in the exponent, right? So this is really tau 2 square to the power t. So it doesn't matter whether we write tau 2 or we write tau 2 absolute value, right? Because I'm squaring it. It doesn't really matter which one we use, right? Okay, so this is the measure. So what is this saying? This is saying that the distance between the current measure and the uniform measure is controlled by tau 2 to the 2t. Okay? Now, does this mean that you will get to the uniform measure as you let t go for a long time? Think about what you told me about where the spectrum lies, right? So the spectrum of the walk matrix. Yeah. So let's look at a picture here. So this piece that you just told me, right? This piece. This is telling you that the spectrum is between, so tau 1 is 1 by Frobenius, and then here is -1, okay, which may or may not be an eigenvalue. We don't know if it's an eigenvalue. But what we know is that everything, all the taus lie here. All the tau i's lie between -1 and 1, okay? So what happens if you take tau 2, which is the second largest thing in eigenvalue, so it might be here, this may be where tau 2 is, right? Maybe 0 is in the middle, here's 0, okay? So in terms of absolute value, let's say tau 2 is sitting there, and then the rest are maybe, I don't know, let's put, instead of putting this, let me put the next one here, and the next one here, and the next one here. So this is tau 3, this is tau 4, and this is, say, tau 5. Okay? So it's moving inwards when we're ordering by absolute value, right? So will it converge in this picture? If the tau 2 really look like this, if you apply to that theorem, what happens if you start taking powers and powers of something that is below -1? It'll converge, right? It's getting smaller and smaller and smaller as you square it. So as time goes to infinity, this tau 2 to the 2t is going to go to 0, right? So if tau 2 is, so consequence, corollary, if tau 2 in absolute value is less than 1, this implies that you will get convergence. Is that okay? Okay, what happened in the cube graph? Why didn't it converge?
One more consort method.
So let's have the non-spectral graph theory answer for a while, okay? Okay, all right. So yesterday we did a bunch of things with the cube graph, right? Yeah, thank you, Lavanya, but let me, I'm going to push the other people to answer. Okay, so what happens? Somebody who didn't see anything till yesterday, please answer. What do we know about the cube graph? What is, sorry? It's bipartite, excellent. So what do we know about its top eigenvalue and its bottom eigenvalue? Mu1, mu_n.
Minus of each other.
Well, they're minus of each other. What's the top one? I want the walk matrix of the cube graph. 1. All walk matrices have top eigenvalue 1, okay? So what's the bottom one for the walk matrix? -1, right? So then what happens to this convergence? So in the cube graph, tau 2 of the walk matrix is -1. That's what you just told me, right? Because tau 1 is 1, and yesterday we said bipartite graphs have symmetric eigenvalues. So if the top one is 1, the bottom one is -1. So tau 2 is -1, right? Then what happens in this theorem? So what happens to tau 2 to the 2t? So this is -1 square times t, which is equal to 1 to the t, which is 1, okay? So what happens to convergence? Do you get it? No, right? It's saying that mu t minus the uniform measure is bounded about by 1 all the time, for all t, okay? The fact that it bounces back and forth is something more special that Lavanya told us, but it's, that requires something more. But at least it's going to show you it won't converge. Is this true for all bipartite graphs? What, this analysis we just did? 1, everybody agree? For any bipartite graph, if you look at the walk matrix, well, in general, the top eigenvalue is d and the bottom is -d. If you go to the walk matrix, it's 1 and -1. And -1 is the thing we got to stick into this theorem. It's never going to converge. Everybody okay? That's why it bounced back and forth. Is there a good reason for why it bounces back and forth? Maybe Lavanya, you know? Okay, let them say. Good. I don't know. This is not we can skip it if that's too hard. But do you see why it bounces back and forth? So it seemed like it was, sorry?
It's -1 in class 1 or something, so it's going from there.
So let's say this is one color class and this is the other color class, right? So if I'm standing here, what's your name?
Vishal.
Vishal. Okay, so Vishal decides to send all he has to distribute his probability, right? He has some probability, and he distributes a piece of it there, and a piece of it there, and a piece of it there. But he sends all his probability over, right? He didn't lose any money. He just didn't keep anything for himself. So he sends everything to the other side. And then everybody in this side of the class also sends everything to the other side. And then those people will send everything back. Do you see? That's what's happening in the cube graph. Good? So that's why it bounces, but the problem is this tau 2. This tau 2 is just 1, is -1. Yeah. Okay, sorry, question? I mean, it doesn't guarantee divergence, but it doesn't guarantee convergence. Okay, so it may converge because it has some. This is just a bound, right? But the theorem doesn't guarantee convergence, right? If tau2 was less than -1, you would be guaranteed convergence. But for a bipartite graph, we don't know, right? I mean, I think it will never, right? I think it'll never converge, actually, for a bipartite graph. Is that right, Lavanya?
Not by using this thing.
Yeah, but by the argument we just made, right? It shouldn't converge. I think it should never. It never converges, right?
The results.
Other results, yeah. Yeah.
If in Fourth Law they are only saying that the measure that is obtained at step T and its difference with the
Uniform.
one is bounded by 1 always.
Bounded by
In
the.
case of cube graph.
Yeah. That's right. That's right. So from this, you can't immediately see that it doesn't converge. But it doesn't guarantee convergence. It doesn't guarantee divergence either. Right?
This is not something that, this is called a periodic chain. So the probability, I mean, it's going to split in this way. For convergence, there's something, another property called aperiodicity.
Yeah, good question. Thank you. All right, so let me ask you, so what I want to do now is to think about how we can improve this theorem, okay? So let me ask you a question. So here's a question for you. So can we guarantee convergence or can we improve the convergence rate? Let me just say that. So can we improve, so this is called the convergence rate. Okay, so can we improve the convergence rate? By choosing a different initial measure. Okay, so typically in this four-claw theorem, we are starting the random walk at one vertex. Okay, so mu0 is just like a E1 or like a EI, right? It's a unit vector. But if I choose a different initial measure, so let's say I'm willing to start the walk from 2 places, or 3 places, or 5 places. Okay, I put a fourth of a measure here, fourth probability here, 3/4 there, and then I start the random walk. Can we do better? Can we get a better convergence rate? Can we improve this theorem? Okay, so that is the question that we want to ask. And it's not really clear what to do, right? So one obvious answer is, easy answer is yes, you can definitely improve the convergence rate if you just start with the uniform measure, right? If our initial measure is the uniform measure, then of course there's nothing to do, okay? So easy answer is choose mu0 to be 1/n, okay? Then we have immediate convergence. But the trouble with this measure is that it's supported on the whole graph, right? If I have to like choose the whole graph to start the walk, so I cannot, so if we're trying to like spread something, or if you want to think about, I don't know, there's negative and positive applications. So if you think about, for example, how disease would spread through a graph, usually there's like a patient 0, right? That's our initial measure. Patient 0 then spreads it to people next to him, next to them, and so on and on. It keeps going. But if everybody had COVID to begin with, immediately at the same time, then of course everybody has COVID, right? But maybe we need a positive example. What's a positive example, Arvind? So we want to allow a little bit more we want to allow the support of the measure to be slightly bigger than 1, okay? So let's say we are spreading something else, like we're
Visiting villages.
Yeah, exactly. You need to distribute food to a whole bunch of villages. If one person starts and then randomly walks from village to village to village, he or she will eventually get to all the villages. But if two people started from two corners, it could be that you will achieve convergence much faster, right? So it makes some sense that you might want to have this initial measure have slightly bigger support than just one, okay? So, of course, this is an answer, but this has like huge support, so that is not great. So this is okay, but the support is support of this measure of the uniform measure is all of n. Okay? By support, I mean where do you see something positive? That is the support. Okay. So let me modify the question. So here is question 2. This is question 1. So the question 2 I really want to ask is, if mu0 is restricted to have support on, so let's say, L vertices. So you pick the L. So it may be 2 vertices, it may be 3 vertices, it may be 10 vertices, okay? You pick the L. If you allow mu0 to have support on L vertices, then what kind of convergence can we guarantee? Or what kind of convergence rate is possible? Okay, so what's your general sense? Does this question make sense? Should you have better convergence rate if you're willing to start on more vertices? Do you expect that to happen?
Do you expect L times faster?
Yeah, we'll see the answer in a bit. We'll see the answer, but I'm just asking just commonsensically, do we expect the convergence rate to be better if we are willing to start on more vertices? Yeah, probably, right? It makes some sense, like the person's, handing out medicines or food in different villages. It makes sense if you have 3 people starting the walk rather than 1 person starting the walk and trying to hit all the different villages, right?
In this bipartite example, if 2 people in 2 different color classes start, then it will be negative.
Exactly. If Arvind and Sudhakar both started sending information, then everybody would eventually get it, right? So it wouldn't bounce back and forth like that. Good. Okay, so that is a question, and I'm going to write down a theorem, which we will prove next time. Yeah, so we already did the bipartite example. So let's write down a theorem that is going to improve the folklore theorem. Okay, let me see where to put it. Maybe I'll put it here so that we don't have to erase it. Okay, so this is a theorem due to, okay, so this is my colleague, Stefan Steineberger, and me, and it's just like 2 years old. I forgot the date. It was, I think, published this last year or something. So this theorem says if G is so let G be a connected deregular graph, or regular graph. Oh, let me not write so many words. So let's just make it short. So I have a G that is connected, regular. You don't really need regular, but it just makes everything nicer. And G has n vertices and some number of edges. Then the claim is that there exists a probability measure, mu0. Okay, so there is a mu0 supported on at most L vertices. L vertices. This is for every L between n minus 1 and 2, I guess, because even 1, I guess. Okay. such that the same difference, mu t minus rho square, is less or equal to lambda L plus 1 to the 2t. Okay, so that's the theorem. No, tau. Thank you. Tau. Okay, so it's all about the walk matrix today. So let's maybe just understand what the theorem is saying. So you pick an L, so it could be 1. Yeah, it can be 1, but 1 is okay actually. It cannot be 1.
G is wide, but
yeah, that's right. It starts in 2, that's correct. Yeah, it starts in 2, you're right. So if you are willing to start in 2 vertices or more vertices, but pick the L you want, then the spectrum looks like this, right? Here is tau 1, which is 1, and then here is minus 1, which may or may not be an eigenvalue, okay? Minus 1 may or may not be an eigenvalue. And let's put 0 in the middle, which also may or may not be an eigenvalue. We don't know, okay? But this is the top one, and then typically the next one is like maybe here. This could be tau 2. This is what the folklore theorem is dealing with, this one. But the next one is smaller in absolute value, right? So maybe the next one is here. This is tau 3. And it could be the next one is here, which is tau 4. And then the next one has to be smaller in absolute value, so it could be here, tau 5, and so on, okay? So this is how the spectrum is moving, right? So it's saying that if you are willing to start with, for example, 2 vertices, okay, then you will have convergence given by tau 3. That is what this is saying, right? If you're willing to start on L vertices, make this initial measure mu 0, start on L vertices, then the bound on the top here is given by tau L plus 1, okay? So if you're willing to start on 2 vertices, tau 3 will be the thing that's controlling the convergence rate. If you're willing to start on 3 vertices, tau 4 will control the convergence rate. If you're willing to start on 4 vertices, tau 5 will do it, and so on, right? So it could be that these numbers, that like tau 3 could be a lot smaller than tau 2, right? So you're going to get much, much, much faster convergence by choosing to have your measure start on more than one vertex, okay? So that is what the theorem is saying. Now, the key to the whole thing is there exists a mu 0 supported on, okay? Supported on L, at most L vertices. So this is key. It's not that you can start in any L vertices. There exists a special way to choose L vertices to support your initial measure. In fact, there are many choices for these L vertices so that you will get this theorem to work. Does this make sense? And these are exactly these graphical designs that we will define in the afternoon. So you'll see that, you know, there's this thing called a graphical design that you can find on graphs, and those have an application like this. So I wanted to start with the application so you see why we care about these designs that are coming later.
So
okay.
There exists L, or when you choose L, there exists mu naught. What exactly is existing?
So you can pick L, okay? So let me put this here. Exactly. So for every L between 2 and n minus 1, there exists a mu 0. So you can pick your L, then that gives you this mu 0. Yeah, Lavanya.
L could be 1 also, right?
No.
No, we are only talking about the bound here, we are not talking about the convergence. We are only talking about bound.
Yeah, that's true. In that sense, yes, right?
No, because this will go, that will become tau 2, no?
Yeah, but that is that.
Folklore theorem, right?
She's right, I think.
Yeah, okay.
Yeah, you're right. You're right. You're right.
Support thing that do not supported on L.
It'll be supported on one vertex, and it'll be controlled by tau 2, which is the folklore.
But convergence is not the attribute.
That's right, right. I'm not even saying that this will, I'm just saying the convergence rate. Yes, you're right, you're right. Okay, so let's put this back to 1. So it subsumes the, thank you. So it subsumes the folklore theorem, but it gives you this extra. And as Arvind pointed out, in a bipartite graph, if you're willing to start on 2 vertices, one person here, one person there starts to walk to people who you are connected to on the other side, then everything will spread and you will actually get convergence. Okay? So as soon as, so it's very rarely that in a bipartite, okay, whatever. But the third eigenvalue, for example, is typically can be less, okay? And you can find graphs where it's drastically less, or the fourth eigenvalue is drastically less than tau 4. So you look at the spectrum, and you see, okay, what is like a small, very, very small eigenvalue? And that might give you an idea of how many vertices you should start your initial walk on. Make sense? Okay, so this is a theorem. And so we will prove this theorem in the next session. That is the key idea. But the way we're going to prove this is going to use convex geometry. So this is the first example where we're going to depart from spectral graph theory and we're going to enter the world of convex geometry. So today we will talk about cones, Farkas lemma, which maybe some of you know if you know linear programming, and we will prove the theorem. And then tomorrow, and then later in the afternoon, I will introduce designs, which are the things that are going to tell you these measures. And then tomorrow we will do more convex geometry. We'll do polytopes and something called Gale duality and so on. Okay, so today and tomorrow is the world of convex geometry. Thursday will be the world of semi-definite programming, which is convex sets, but they're not polyhedral. And Friday we will continue with that theme. Okay, so these are like the geometric parts. That's the geometry in the title. So today you'll see graphical designs and convex geometry and various applications of it. So the proof entirely depends on geometry. Okay, so that's what's coming in the next session. Shall we stop for now?
Yeah.
What about that also?
That you can, once you see the proof of this, you can prove.
Originally the
It's not done through geometry. No. How do you know how that's proven, Arvind? It's not geometry, right? No, it's not geometry. So this one we will need geometry.